Good evening, everyone. So, in today's lecture, we would be considering in detail about the ARCH model, which is known as autoregressive conditional heteroscedastic models. So, what is the ARCH model? Where it is useful? So, this whole idea, we call this as volatility modeling, and the application of this is basically in financial domain. So you can have, this can be applied in option pricing. Now, details about option pricing you're going to learn in a course next semester if you're taking stochastic models in finance. Most of them. In fact, this now item 1 and 2 will be discussed in details over there. So we won't be actually explaining each of them because that will take, in fact, that is actually the syllabus of that. So the risk management and value at risk, that means risk management means basically, you need to have a particular value which consolidate what is the maximum loss that you are going to have in 10 days trading or in 10 days transactions. So that is what basically the value at risk and expected shortfall. And then you will also have the capital asset pricing model, CAPM, which is basically connecting the individual stock to the market price or individual stock price to the market stock price in under a regression setup. And then you have portfolio management. Portfolio management in the sense that I have some money, so which are the stocks that I should buy and how much I should buy. So this is basically on portfolio management. So in all these areas, this volatility is important and useful. So that's what whatever we are learning, it will be useful over there. Now, this is not directly observable, as you can see that we are working or we are looking at the conditional variance as opposed to the marginal variance, and that's it is not directly observable, and this is a kind of implied, and you can see that this implied idea is will be discussed in BSM Black, Scholes and Merton formula, which is basically the price of an option uh, to be, what should be the price of an option with a specified period of time and specified initial value, etc. Now, basic properties of these are volatility clustering, which evolves over a time in a continuous manner. That means once you have the volatility, it continue to be volatile. So that's what the clustering does not diverge to infinity. But that doesn't mean that actually, keep on going up and down. And is there any possibility that it will go into infinity? It will not happen because it has a mean reversion property. It come back to the normalcy. So it won't go to infinity, and often this is basically a stationary kind of series. So you'll be wondering how it is possible, because you are trying to model some variations, and then as per time, then how that remains stationary. In fact, that is the beauty of this whole model. The marginal models are stationary, but the conditional variances are changing over time, and then that accommodates the variations. So that's what we are trying to model in our context, and what is called as conditional heteroscedastic model. So the SEF PSEF of, so what you should look at to know this. So you should look at the ACF PSEF of absolute and square returns, because absolute and square returns show the dependence of the arch effect. So basically, in the usual analysis, we look at the ACF PSEF of the returns as such. Now you should look at the absolutes or the square, which basically talks about the sigma t square, which is the conditional variance. Now, deterministic volatility model, this is the model that we're going to discuss is not like a regression. It's deterministic in the sense that certain observations at the time point t are known to us, and this is going to be a function of those observations only. So you can imagine how difficult it is going to be. Let's look at what is the model building strategy. So in the usual time series analysis, the model, the conditional mean. So you have the conditional mean, ARMA, ARIMA, seasonal ARIMA, etc. These are modeled for the mean, and then you try to get the residual from there. So if I want to explain this using your this. So what you have is basically you have some kind of a series, and then you have this mu t, and then you have this epsilon t. This is what the conditional mean, which is expected value of yt given ft. So you have this expected value of yt given ft minus 1, sorry. Now when I say ft minus 1, this is basically the information available yt minus 1, yt minus 2, etc. towards all the past. This stands for the sigma field, but you don't have to bring in the sigma field as such here. It essentially means that the information available at these past values. Now we are trying to, this model, this, the conditional mean, this mu t, and this is what we have learned so far. So the mean modeling basically uh, talks about mu t. Now, what we have in this case is like this job is done, and what you have is now yt minus mu t. So I'll put a cap here to indicate that the job is done. And this is what you have the epsilon t's now. So essentially speaking, this is not there in the sense this is already taken care, the mean effect of that. And then what you have is the residual. So now our model is going to depend on, I mean, this is what uh, that you are trying to model. Now, for example, if this is not there or if it is a constant, this is pretty simple because then you can, this itself is white noise, 0 sigma square. So you can say directly that this epsilon t, the observed or the return itself is like a white noise. So we are trying to model them. So there is no need of doing this. But that is very special cases. You can see that. So when you do the data analysis, you can see that some of the YTs behave like epsilon t. So no need of taking care of this. But if you need to take care of that, we go through the mean modeling, and that's what we have learned in these steps: ARIMA, ARIMAS, ARIMA, etc. Okay. Now, how do you know that we need to go for the variance modeling or the conditional variance modeling? So they use this residual. Uh, See, this is our residual, this epsilon t, and our marginal. So as per the assumption, you have 0. Sigma square is the variance. This is marginal variance. Marginal variance, which means the expected value of epsilon t square. But we are not modeling this because this still remain the constant because you have a stationary process. What we are trying to model is the conditional variance. So I am going to now call this a sigma t square, which is expected value of epsilon t square given ft minus 1. Or you can write it as expected value of yt minus mu t whole square given ft minus 1. So this is what the conditional variant. So we are basically trying to model this rather than modeling. There is no model for sigma square because sigma square remains just a parameter, it's constant, whereas this varies across time. So we need to have an appropriate model for sigma t square, and that is what called the heteroscedastic modeling. So we'll check the fitted model with carefully and refine it if necessary. And then, so the steps involved is that specify this model, a volatility model, and then perform the estimation of the mean and volatility equation. And once you specify that, you carefully examine it, and then you need to do the forecasting of the series, and then you can also forecast the volatility, which is of independent interest. The reason being that many people would like to know how the market is going to behave. So because volatility sort of indicate, the variation in the series. So I would like to know how the series is going to vary. Okay. So there is an independent interest for modeling the volatility as well. So let's look at the model now. So as I was telling, this is like I have RT. I'm changing the notation from YT to RT. RT is equal to you have mu t plus epsilon t, and as I told you, this This mu t is nothing but expected value of ft minus 1. Ft minus 1 is in the similar way. I've just changed the notation from yt to rt. And then you have, I need to estimate them, model this with the appropriate. For example, one model could be like, something like phi naught plus phi 1 yt minus 1. This is an AR1 model. So I'm getting mu t in this manner. It could be depending on, I mean, MA, seasonal arima, etc., etc. But all, this is what the mean. Now, if you look at this, so look at this carefully. How do you actually see whether there is a need for the variance modeling or the conditional heteroscedastic modeling? So this is called what is known as arch effect. Does it has that property? So the property is identified basically by looking at the ACF and PACF of absolute or squares of residual. Now, once this modeling is done, we have the residual. What is the residual? Epsilon t hat is rt minus mu t hat. So you have this residual, and for this we will be getting the ACF PS. Of course, you will be all directly getting the ACF of this to see that whether the model is correct. So that you already learned that we will do that. But it may so happen that here all the the time points, the ACF and PACF are well within the control, those two lines. But when you start looking at absolute or squares, so the absolute, sorry, so when you start looking at this or when you start looking at this, now why do we look at this? Because the squares, because the mean is 0, the squares represent the standard deviation and variance. Because this represents standard deviation, this represents the variance. So we are trying to see whether it has a correlation effect across the time, and that's what we are trying to see when I say I look at the ACF and PACF of these squares or absolute value. So okay, so here apart from those things, so what were the steps in the earlier modeling, mean modeling? You have to come up with a mean functional form here using some ideas and then estimate the parameters. And once you estimate the parameters, identify whether the fit is good. If the fit is good, this will behave like a white noise. And how do you identify that it is a white noise? You plot the ACF, PACF, and if they are within that uncorrelated mean 0 and a constant variance, then you say that this is a white noise. Now that is where we start our procedure now. Because it may appear that this epsilon t hat is like ACF, PACF are well within those upper limit and lower limit, but this one and this one is actually significant, will turn out to be significant. So that shows that there is a need for conditional heteroscedastic modeling. Okay. So we should look at always this and this. Oh, this doesn't require a square, I mean absolute value, that is already square. So look at ACF, PACF of this. If significant, then we say there is a arch effect. Arch effect means autoregressive conditional heteroscedastic. Let's go back. Now there are some statistical tests available for this. One is, of course, you know that because you are looking at the correlations. So one test that we have learned already is a Limbox test. Limbox test is basically summing the autocorrelation, estimated autocorrelations, and dividing appropriately so that you can have a distribution theory attached to that. So now what you do, you look at this to this series. Now this series means this series you will obtain the given series itself is square of the given series itself is this, provided this mu t is not there. If mu t is there, you do the mu-t estimation or modeling and then subtract this, then you will get the epsilon t. Okay, and what we are saying is the lags of epsilon t square series are 0. That is what we were investigating. So in the Lagrangian multiplier test, what we do is that you consider an F statistics, because we're trying to look at a regression model like this. That means the square of epsilon t is actually depending on t minus 1, t minus 2, etc., t minus m. And then I would like to test the hypothesis that alpha 1 equal to 0, alpha 2 equal to 0, etc., alpha m equal to 0, against that at least one of them is not 0. And this is like a typical regression testing hypothesis. So one can obtain those tests, the sum of squares of restricted and unrestricted, and then you can get the corresponding F statistics. And we know that this is a chi-square distribution. Of course, there is some problem here. Epsilon t's are not necessary IID but uncorrelated, but still it is possible. But if you assume that normality, then they are IID kind of assumption, so that you can have all these things. Now, even if it is not normal, you have the similar kind of an assumption with the white noise, still you get this kind of thing. So F is asymptotically chi-square with m degrees of freedom under H naught. Under normality, we may consider F with this, and then C. So this is actually a test to test that any of these are 0 against that they are non-zero. So if they are non-zero, it means that these fellows are influencing on this, which means that the variances are being influenced by the past variances. That is what the conditional heteroscedasticity is. So this is a statistical way of testing. A graphical way of testing is look at the ACF and PACF of squares or absolute. Okay, let's go ahead. So the model is given by, so what that we are trying to model. So these are called a class of multiplicative models, because I'm trying to have your RT is equal to mu t plus epsilon t. So this part is done, and now we are trying to model epsilon t. So it is like an error, but then I'm not interested in changing the mean, whereas I am interested in changing the variance. So I would say sigma t z t, and then try to give a specification for this. So make a specification like something like alpha naught plus summation j equal to 1 to m alpha j epsilon t minus j square. What are these epsilon t minus j square? So these epsilon t minus j squares are the residual, or these observations which are available at the time point t, because you will be available t minus 1, t minus 2, t minus m. And this is something which is not like in the usual regression problem, because in the usual regression problem, this is a response, this is observable, whereas in our case, this is not observable. This is like a conditional variance. So you are trying to model the conditional variance, which is not observable. See, this is very important. So we are modeling the conditional variance which is not observable. So you remember, now in the usual regression setup, you have a plus an error here, but there is no error here. That's why it is called a deterministic model, because at the time point t, all these are known to me. So these are known factors or known numbers. So this is a kind of deterministic equation. Now this is called a multiplicative model, because here we are not adding, right? Because epsilon t, this is observable, epsilon t is observable. Don't confuse with your usual epsilon t is an error. It was an error here, but once I estimate this is observable. I know these values. So I have this with me. Then I'm trying to model this and then try to get this fellow out of it, which is basically creating problem. And once I do that, because this ZT, we assume that this is IID with mean 0 and variance 1. Well, IID is a very simplified assumption. Some people start with white noise, but I would say you can go for the IID. And we are not leaving out any parameters over here so that we don't have to estimate them. So what is required is the parameters which are coming in the specification of this conditional variance. Now, how to specify this conditional variance? So the conditional variance can be specified as in terms of the past error squares, and that is what we are trying to do. So look at this particular expression. So what you have is here, the condition, the variance is like alpha naught plus alpha 1 epsilon t minus 1 square plus etc. alpha m epsilon t minus m square. So this is what the conditional variance, sigma t square is this variance. So I'm trying to make a specification or a particular formulation of this, right? And I think I already mentioned ft minus 1 denotes the information set available at time t minus 1, and set t is r IID normal 0 1 student IST generalized error or generalized choice of ZT. You can have different distributions for ZT. You can have different distributions for this. Now, if you specify this model in this format, it is possible to see that the expected value of epsilon t, epsilon t can be substituted by sigma t zt over here, and then this sigma t is a function of, because this once this is given, all these fellows are constant, so it comes outside that, right? So this sigma t comes out as this expectation, and then you have expected value of zt given ft minus 1, and then we know that zt is uncorrelated with ft minus 1, therefore expectation of zt is 0 because zt is IID 0 1. So you have this is 0, and then you multiply, so you have the 0. So this is the marginal mean is 0, and look at the marginal variance now, variance of epsilon t. So variance of epsilon t, you can now see that it is the expected value of epsilon t square, because expectation of epsilon t is 0. And expectation of epsilon t square, I can write it as expectation of epsilon t square given ft minus 1, and again take one more expectation. So this is called the smoothing property of the conditional expectation. Expectation of x is equal to expectation of x given y. Exactly the same thing which we are using here. So you get this particular one, and then I am going to substitute for this fellow here. Epsilon t square is sigma t square zt square, and this sigma t square comes outside. So I have expectation of zt square, which is 1. So basically expected value of sigma t square. And now we can show that this expectation of sigma t square. So what is sigma t square? Is alpha naught plus alpha 1 epsilon t minus 1 square. So if you're talking about Garch 1, if you're talking about Garch M, it is all these terms are going to be there. In such a case, this turns out to be, because you are going to have the same thing on the left hand side and right hand side, because this turns out to be epsilon sigma t square, and then I have sigma t square is coming on this side, so I have these quantities, and you are taking the expectation of the square of this quantity. Square is already there, sigma t square, so direct the expectation of this. And if you are taking the expectation, you can see that this turns out to be, I'll send you, this can be verified here also, like for example, if you can have a model 1 and you can actually compute this and then see. So what we have is expectation of epsilon t square is equal to variance of epsilon t, and then this we have now said that this is equal to sigma t square, which is alpha naught plus alpha 1 epsilon t minus 1 square in the case of arch 1. So this can be now written as alpha naught plus alpha 1 expectation of epsilon t minus 1 square. Now you see that this and this are same whenever you have the stationarity. So I assume that you have stationarity. We'll discuss about the conditions of that, which implies expectation of ft square is equal to alpha naught 1 minus alpha 1, or variance of epsilon t is equal to this. Now if you're talking about arch M, this will be alpha naught upon 1 minus alpha 1 minus alpha 2, etc. minus alpha M. So this is what this derivation is all about. So restriction on parameters are, now what happens that if you're talking about arch M, there are m plus 1 parameters which include this and this. Now this has to be positive The reason being that you are talking about the variance, so this has to be positive. This can be zero, some of them can be zero also. So, but this has to be positive. So strictly greater than zero, alpha naught, whereas this can be greater than or equal to zero. Okay, because if these are all zero and if it is you are not allowing that to be strictly greater than zero, all will be zero, which means that the conditional variance is zero, which we are not interested. So restriction on the parameter. Now what happens that if you start getting higher order moments for this epsilon t process, then we have to put more restrictions on these parameters, the area in which it be vary. See, for example, in this computation, you have seen that so I have to have alpha 1 less than 1. I cannot allow alpha 1 to be greater than 1. In fact, you will see that now if I go for the third moment, alpha 1 not even 1, it has to be less than 1 by 3. So such kind of restrictions we may have to. Yeah, so here I have made the computations for m equal to 1 with normality assumption for zt. The fourth moment of this expected value of sorry, epsilon t to the power of 4 ft minus 1. You know, the fourth moment can be computed under the normality assumption as 3 times of this, which will give me this. I'm doing this computation for m equal to 1. That means I'm computing it for arch 1. So you get this 3 times of this. Sorry. And the 3 times of this, now in this there will be a term epsilon t to the power of 4. So I need to get that fellow also computed. So this to the power of 4, again I use the smoothing property of the conditional expectation. And then you can, now what I do is that I'll substitute for epsilon t is sigma t zt. So if I do that, I'll be in a position to arrive at this quantity 3 alpha naught square 1 plus alpha 1 1 minus alpha 1 1 minus 3 alpha 1 square. This is not difficult. You have to just substitute here and then simplify. So if I do this, we can get the kurtosis, which is the fourth expected value of epsilon t to the power of 4 divided by variance of epsilon t square, which will give you, you simplify this, that will give you some quantity like this. Now since alpha 1 is less than 1, in fact alpha 1 square is less than 1 by 3, you can see that this whole stuff is, because otherwise you get negative, so we don't want negative here. So this will be greater than 3 because there is a 3 here, so this entire quantity will be less than 1. So this implies that the tail of the distribution of epsilon t is heavier than that of normal. How did you get that? Because if you have this thing less than 1 by 3, that comes from here, because you want it to be positive. So alpha 1 square has to be less than 1 by 3, which means that this will be, greater than 1. And greater than 1 means the kurtosis is greater than 3, because there is a 3 here. And kurtosis is greater than 3, it shows that you have heavy tailness here. So even with the normal innovations, you can see that the epsilon t process is like a heavy tail distribution. So now there are a couple of issues here. So arch process has fat tail even with normal innovation. In other words, the fat tail is a result of the volatility clustering as specified by the arch equation. Now one of the issues here is order determination. Now when I say order determination, it means that how do I decide how many of the past error squares needs to be considered. So that is one thing that we need to worry about. And of course the estimation also is there. So we need to estimate the parameters. So you can see that this is a simulated Arch 1 model, simulation of size 500 with omega equal to 1. This omega actually stands for, in our notation, it is alpha naught. And alpha equal to 0.95, eta t is zt, normal 0, 1. And so you can see that these spikes, this is where the volatility happens. That means the price, if it is a return, suddenly the return goes very high, the return goes very low. So this is where the volatility happens, or the variation happens. This should not happen actually. So if this happens, how to model it? Still I want the series to be stationary, because even after coming here, it has come back to its normal position. That is what called the mean reversion. It has, even if it has gone here, it did not go like this. The reason being that it is stationary. So You have to make them hold them as stationary, at the same time allow this, and that is possible only by looking at the conditional variance. Okay, so this is where I think I'll stop at this point, because otherwise we will not be in a position to complete. We'll continue with another video. Okay, thank you.